everyone. Welcome to episode number 31 of this Amiga 68,000 assembly programming series based on the book of Fabio Ciucci, whom I thank for giving me the permission and letting me stream his book. I mean, I could have translated the book. Some people suggested to me to translate the book, but translating the book would have taken longer than doing the streams. So this is one of the reasons why this streams has taken place. And also, I think most people prefer watching a video and seeing exactly what one can do. Let's continue with the book. So I'm going to show you, let's go on the Amiga. I'm going to show you what we did last. So we had this, we were plotting pixels to the screen, and the last thing we did, we were reading from a table and plotting the pixel, let's say, based on that pattern. And as you can see, I can press the right mouse button and it doesn't erase. And if I remove my hand from the right mouse button, it will start erasing again. That was our last example. Actually, there was another one, which is not actually part of the book, but it is something that Fabio included as one of his students did, which happens to be a member of Phase 101. So, and that is this one. Which is also plotting a pixel, but reading from a file, and this one is able to handle colors. So we did these two. Now, what's coming next? Okay, we're going to cover copper bars. Okay, he doesn't give a full explanation of this one. I am going to give a full explanation of this one. So this is the advantage of you having me and not just the book. Because, as I said, the book, he did not explain this. He just explained some theory, which I will come to it. Right now, let's see it. Please note that my emulator is not optimized for A1200 or for the A500, but it is optimized for me as a developer. So you might see some glitches, okay, but it should work. And that is the copper bars that Fabio is showing us. Notice, I don't know if you'll manage to catch it on the screen. Maybe when you're watching the video, you can slow it down or you can pause it. But each color, okay, there are lots of shades of the same color, but each color is two raster lines. I'm telling you this because I'm going to talk about it in a minute. Okay. Also notice, as I said, when the copper bar goes up to the screen and then going down, you might see some. I'm noticing some flicker here. I don't know if you will see it on the stream, but it's because I have a faster CPU and it's handling things a bit differently. But it shouldn't be a big issue. It's just these sources were tested and optimized and made sure to work on an A500, A600, and an A1200. At that time, Fabio did not have an A4000 or an A2000, so so yeah. But as per book, it's guaranteed, all the sources are guaranteed to work with the 68020 standard A1200. Let's jump back to the book. So far, so good. So copper bars, and with it the example that he's showing here, this one, the Lezione 80. Okay. Now, why he didn't go into the detail of explaining this code, but he just wanted to explain one thing. Instead of creating a copper list for our copper bars with a color changing every two raster lines, he is saying, why don't we build this through a simple program? And that is what he did. And he's showing us how to do that. This is the routine that builds our copper. Basically, in the memory that we allocate, this is what it inserts. Okay, what we have down below. Okay, but notice what it is doing. It's moving. Okay, I mean, bar copper is where we are storing our copper bars. Okay, so it is, let's interpret these two lines, okay, which is line 5 and line 6, the move.long. The first one is a wait at line 30, okay, and you know that FFFE is a wait, okay. Then the next one, you know that 0180 is color register index 0, okay, and we are moving 0 black color to this register, to this index. And this routine, okay, moves those values into the 80, which points to bar copper, and then adds this value, okay. And why this value? Because to the 1, okay, only to the 1. So here we are adding that value. So basically this number will become line 32, okay, and still 1 FFFE, sorry, FFFE, okay. So line 32, okay, raster line 32 and FFFE, and then it will become 34, etc, etc. So this is what the loop is doing, and somewhere, I mean, I will show you the code in a minute. Somewhere in the code, okay, he has this routine, and we are building the copper list before we actually display it. Of course, he has other routines to move the copper list, okay, the copper bars, but he is not explaining that. That I can explain. It is not a major thing if you do not understand it. It's not something that you need to, you know, beat yourself in understanding that. However, the code is not difficult. The reason why I'm saying that is because the routines, okay, you should be able to understand them, but the most important thing is that you understand the concept of building the code, these copper bars, using code instead of entering it one by one. That's the most important thing here, okay. To be fair, the routines, we have used them in the past, okay, but still, if you do not understand the thing, it's the concept that is important. When you have such a thing, you just need, instead of, and it will be a tedious job entering all those numbers. There are 8 or 9 copper bars there with all those shades of color, entering them manually. So might as well, since it's a repetitive task, let the computer do it for you when the actual program starts, because it's the first thing that it does. Okay. I'm just checking if there's anything else to say in relation to that. So no. So let's go to the, now remember we have 2 books. We are in the theory book, and let's go to the example book, and we are in example 8.0. So branch to subroutine init copper, okay, is the routine that you just saw. Okay, it is adding that value, okay, to this, to the value in the one, so that we built our copper. If we see bar copper, we will find bar copper. You know, I'm referring to this, not this here. Okay, I'm referring to this. It should be in the copper list. Bar copper, here it is. I didn't highlight this, but notice the define constant word. Sorry, not define constant block. Okay, and it's a word. And basically, how many copper lines we have. So somewhere we have defined how many copper lines we have times 4, because remember it's words. Okay, so we need 4 words to define one raster line. Okay, to change one raster line. And basically we create, we allocate the memory like this within the copper bar, within the copper list. My god. Few other things that I need to mention before I continue to explain the code. Here we have a table that was generated using the is command in this case, but I prefer using the cs command. The reason why is the is command, you don't see what is generating, you just save a file. But the cs command, you see what is generated. So I prefer the cs command instead of this one. Notice that from 1, 2, 3, 4, 5, 6, from here to here, okay, is one set of numbers. So it's a curve, no? Is one set of numbers, but then if we have 6 here, 55s, we should have, sorry, 1, 2, 3, 4, 5, I should have said. So here there are 5 55s, and there should be another 5 55s, okay? Then we have 54s, and 54s we have 1, 2, 3, 4, and we have 1, 2, 3, 4. So it's the opposite way. And this is what, if you remember, what the cs command or is command, they generate sine waves, okay, for us. And this is our plotting routine of how we are plotting our copper bars. This is the colors for each copper bar. We have 8 copper bars, so there are 8. I said 9, I think, but it's 8. Okay. Each one of them with 13 colors, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So there are, each copper bar has got 13 colors, 13 shades. So if it's yellow or blue, there are 13 shades of that color. Okay, and this is how he fills the copper bars with those colors. Now, also, we need to have a position of where the copper bars are, and this part is the position of where the copper bars are. Okay, where they start, or the offset from each other. Now, just before I explain what he is doing, okay, I explain this part that fills up the copper bar, the that creates our copper bars. But then to move them on the screen, okay, and see them moving on the screen up and down, you need some type of routine. So basically you are displaying them, erasing them, and drawing them at, let's say if they are at the top, at a lower position. Okay, so there's another routine, okay, that is, I do not want to be here yet. So this is the one that I covered, init copper. Now we wait for raster line 108, okay, and then, so this is our wait for position on the screen, okay, and then we do the, as you can see, he called it clear copper, because once you draw it you need to erase it. So here we clear the copper, okay, so we find the routine clear copper, which is this one, and basically it's clearing the copper list and make everything black again. Okay, it does, we don't see it because it's happening while it's not being drawn. Okay, then he has another routine where he moves the bars further down, let's say if we started from top, and he fills them again with the colors. So we erase them from, we made them with black color or blue color in this case because the background is blue, and we fill them with the colors. That's basically it. Okay, now he has another routine, which I believe is this one. This is that moves them. Yes, this is the routine that moves them, okay, that moves them down, let's say if they are going down, and then this is the routine that copies the colors into the copper bars. Okay, these routines we have covered in the past, and please note that they are a copy. Okay, so this one, okay, here is the same, should be the same, let's put it this way. No, sorry, not here. See, I was going to make a mistake. This is the routine that copies the colors, and it's just a loop that goes through all of them and copies them. But this should be, yeah, I believe from here to here, okay, these repeat. Okay, so it's doing it for each copper bar, it's doing the same thing. Basically it's moving them one down depending on what it reads from the table. Okay, so the value is getting it from the table, but it's a repetition for each bar, and you can see that there are, so this is bar 1, and you can see bar position 1, and we should end up with position 8, as you can see. So these are, as I said, the same, just copied 8 times. And as I said, this is the one that is copying the color. So now that we've seen these this example of the copper bars, remember I said he's adding 2, and I showed you that he's adding 2. But what happens if we add 1, and what happens if we add 3? Okay, so if we add 1, you can imagine that the copper bars will be smaller, and also they will not move till the bottom of the screen because the movement is shorter using the same routine, because we have defined, we do not change the value. Okay, but if we tell it to move 3, okay, it will move a lot further. The only problem that I have with when it's 3, you will see, because of the emulator that I'm using, the configuration of my WinUAE, because it's a development one, you will see some flicker at the bottom, let's put it this way. So let's go to the Amiga. And show you the examples. One which is running at 1. Okay, so this one, we changed the value of 2 to 1. Okay, and you can see the copper bars are smaller now. Each shade of the color is only one raster line. And of course, it's moving also till half of the screen, let's say, because before the movement was a lot, I mean, the copper bars were longer, were bigger, no, in height. So in the program there was, okay, only move, let's say, 100 pixels down. But now 100 pixels down with copper bars which are smaller, it means a different story. So that's one. And this one, it will work, but it will have some issue at the bottom, I guess. As I said, notice it will go down, but because we are using 3 lines instead of 2, I am basically escaping the screen because I remove the borders. Okay, so that's why my emulator is configured without the borders, so that I have a wider screen for the Amiga. That's why I'm seeing this problem. You can remove the borders on the Amigas, you know, but removing the borders caused this issue in this case. So that was the example related to the copper bars, and we go back to the book. Now I arrived in a section in chapter 8, which, as I said, there are no sections in chapter 8 for some reason, and I do not agree. Okay, I mean, Fabio had his own reason at the time when he did it, but I do not agree with this, what I'm going to cover now, to be in chapter 8. Chapter 8 is a is a mixture of lots of things. We had the startup file, we had copper bars, we had plotting, lots of things were covered. here we're going to cover the status register of the 68,000. This for me should have been covered on a chapter, on its own chapter. The reason why is, one, it's a very long one, could have been in a chapter by itself, and he goes into the depth of explaining the flag registers. We have been using these flags already, but we haven't really gone into the depth of how they work or what they do. Okay, so this is why I would have preferred if this was a separate chapter, because, you know, we did chapter 2 on 68,000, and let's say it was for beginners. Now we are touching the advanced part, so he should have done another chapter, in my opinion, in relation to 68,000 code. But this is the way he did it, and since I'm following the book, I will do it as per book. So the status register, okay? What is the status register? The status register is a 16-bit register found into the CPU, in our 68,000 or the Amiga 68,000 or any other CPU, which has flags in it, okay? Let's call them flags. Each bit represents a flag for now. Now, in the case of the 68,000, it is divided in two, okay? And it's divided in two, okay? We have the system byte, as he calls it, or supervisor mode, and we have the user mode or user byte. So the lower 8 bits is our user byte, and the upper 8 bits of this 16-bit register in the CPU is the system byte or supervisor mode, because you can only access them being in supervisor mode. For now, I will not be talking about supervisor mode, okay? It is something that we will cover. There's a whole chapter dedicated to supervisor mode in a way, including interrupts. So I will not be covering that. But we will be covering the user mode or user byte in this case. As you can see, there are 5 bits. 3 of them are not, I mean from 8, only 5 are used. The first one, bit 0, is the carry, okay? The second one is the overflow. The third one is the 0. The fourth one is the negative flag, and the fifth one is the extension or X flag. Each flag is represented by one letter. So C for carry, V for overflow, Z for 0, N for negative, X for extension. Now, we are mostly interested, as I said, in the lower 8 bits of this register. Please note that these flags, okay, so all bits together, okay, I'm just going to click there again. All bits together are the user byte, okay, but these flags all together are called the condition. They are the condition code register, okay. This is where we, from the user in user mode, okay, this is where we make decisions, let's say that. Okay, with these flags, we are able to make decisions thanks to them. So they are called the condition code register. I'm reading through the notes to see if I've missed something from what all our programs will execute in user mode most of the time, and sometimes we need to go to supervisor mode. But as I said, we will come to that later on. So far, we've always run the programs in user mode. If, for example, we are using interrupts, then we need to go into supervisor mode. And there are certain instructions that only work in supervisor mode also. So each instruction can influence the flags. Okay, so every time we are executing an instruction, it can influence the flags. Okay, most of the time. I don't want to say always, but most of the time. Example, if we subtract something, okay, and it creates a negative number, a negative value, then the N flag, okay, is set to indicate that we have a negative value in our register. And based on that, we can make a decision. If a result is not possible, okay, let's say we are adding 200 with 200, okay, 2 bytes, okay, but we are storing it in a byte, okay, it will not work, okay, because a byte can only store up to 255. So then that means the carry flag will be set to indicate that we had that we need to use another byte and move that to move the additional let's say values to another byte. Also the overflow flag will be set because it cannot fit in a byte. There are several conditional code or branches that can do a branch based on conditional codes. So normally they are a conditional instruction is written, okay, starts with B and then CC, but CC, which stands for condition codes, is replaced with one of these where I have CS here. So there are many of these, okay, so it's not, come on, come here, it doesn't want to move the cursor. Trying to highlight, but yeah, no. So here he's mentioning some of them, okay, but there are more of them. So branch on carry set, so there is a B, so the instruction is BCS, okay. Branch on equal, branch on greater than or equal, branch on greater than, branch on high, branch on less or equal, branch on less, branch on some of them are signed, by the way. Branch on less than, minus, and plus. That's something that I will be covering in a second. We use the compare instruction, okay, to let's say make decisions. Normally there is a compare instruction and then we have a branch, okay, but some decisions, okay, can be also made without using a compare. Okay, there's also the test instruction which can test for, let's say, for a bit, okay, whether a bit is set or a bit is not set, and things like that. So there's various combinations of these. I'm just scratching the surface right now, which can influence the flags, and based on what happens to the flags, we can make decision. We can make a decision on one flag, or we can make a decision based on more than one flag. Let's say if we have a C and a V, okay? So we know that there was a carry, but it doesn't fit, so we can make a decision on that. Of course, it is two checks, but still. The X, I'm just going up a bit. This one, the X, bit 5, okay, bit 4, sorry, okay, is normally a copy of the carry flag, okay, except when we are doing binary coded decimal. Then you need to also use different instructions, which I will mention in a minute, but just to make you aware. So I'm just trying to make all this fit in one screen. Yeah. These three tables, if you are ever confused, just look at them. Okay. So here we have a list, the first column here. Okay. The first column here, we have a list of branch instructions. Okay. And we say branch, and we move. First of all, a branch can be an S, okay, so short, so +128 or minus 128 plus 127, or it can be a word, okay? They cannot be a long. That is for the jump, okay? Excuse me, I need to drink some water. So, based on the decision that you want, let's say branch on high, or branch if greater than, or branch if carry is clear, or branch, let's take this one, number 9, branch if carry is set, okay, we jump. So if it is set in this case, then we jump. If it is not set, we continue executing the code. So it's an if then, basically, but using flags. Now, although we have all these type of branches, okay, we need to know that some of these branches work when the value, when the number is just a plus number, okay, from 0 to 255. Let's say if we are working with bytes, and when the number is, can be a negative number, so from minus 128 to 1 to -1, and from 0 to 127. Okay, I will come to how we can have a number like that at a later, soon after this, but for now we can have two type of numbers: signed numbers and unsigned numbers. Unsigned numbers, they are always positive, and signed numbers can have a plus or a minus in front of them. And we have instructions that only deal with signed numbers, that is, they have plus or minus, and instructions that don't. Those with star here means that they are signed numbers. They work with signed numbers. Those that um, are not with a star means that they work with only unsigned numbers, so always positive. However, there are two instructions that work with both, okay, which is the branch on equal and branch on not equal. So this is how we jump, okay, how we so we have an if we had to think of an if then statement in BASIC, okay, we are doing the then part, okay, the branch is the then part where we are going. The if, which is the comparison, is done with the compare, okay, and notice the compare is operator 1 and operator 2, and it's always operator 2 against operator 1, but it's written the opposite way, okay. Is operator 2 equal to operator 1? Okay, is operator 2, okay, different than operator 1? Is operator 2 greater than operator 1? Okay, and it continues like this. And as you can see, okay, this, for example, branch if greater than, okay, it had a compare of operator 2 greater than operator 1, and segno means it is signed, okay, so it can have a plus or a minus. Now, so we had the compare instruction, and based on the compare we branch, okay. The compare instruction is what sets those flags in this case, okay, in an if then statement. Now, as I said, besides compare we can do a test, okay, TST, and it's the same thing, okay. Is it operator 1 against whatever the number? Well, branch on equal, branch on not equal is quite easy to understand, but the others, which are for signed numbers, okay, so TST, okay, these two are unsigned numbers, and these four are for signed numbers, okay, using TST. And all he's doing is whether it is greater than 0 or 0, greater than or equal to 0, less than or equal to 0, or less than 0, okay. That's all what the comparison is of a test. So you can notice the usual symbols, okay, the symbol for greater than or equal, or greater than or equal, or, but instead of using those symbols we have those instructions, okay. Now if we had -1, okay, for signed numbers, we have, and it's a long, we have FFF, I mean 8 Fs, but basically because it's a long. If I'm going to come to how we do this, okay, for now just follow me. If we have -5, okay, we have 7 Fs and a B, okay. In my opinion, these are better visualized as binary, okay, but some people prefer hex. But both of them are a minus number, okay. You tell me how we decide whether a number is minus or not. Well, depending on the mode that we are working in, okay, which instruction we are using. Normally for a signed number, okay, we use the high bit. So if we have a word, sorry, a byte, we use bit 7. If we have a word, we use bit 15. And if we have a long word, we use bit 31 to indicate whether the number is signed or not. The values, as I said, for a byte are plus 1 to 7 and minus 1 to 8. That is the range. For a word, it is plus 3 to 767 and minus 3 to 768. And for long, I do not know it by heart, but it is a very long number. So I don't know if he mentions it here in the book. No, he doesn't. But yeah, that's whatever. I think it's 2 million something. I do not know it by heart. Anyway, so we have a system to indicate negative numbers, let's say when we have a range of minus and plus numbers, which is called 2's complement. Okay, basically we divide our range, if we're working on a byte, in 2. Okay, so we say from 0 to 1 to 7 is plus, and from 1 to 8 to 255 is the opposite, and it is a minus, which will indicate minus 1 to minus 1 to 8. Now, yesterday I did a small chart on the whiteboard. Let's see. So we are working on a byte, okay? We are working on a byte, and let's say we have 3, okay? So to represent 3, okay, this is the number. This is how we represent it in binary. I personally find it easier to work in binary when it comes to these things, to understand it. Okay, now that is 3. So how do we represent minus 3? Before I explain here, I'm just going to jump a little bit here. So with 8-bit, okay, oops, with 8-bit we can represent from 0 to 255, okay? However, if we divide it, okay, we have from 0 to 1 to 7 and from minus 1 to minus 1 to 8. So we have positive numbers and negative numbers in 255 combinations. So we divided the byte basically. So how we do this? Okay, every time I'm making the screen smaller. Okay, so if we had to take this range that we have up here, okay, and write them down, then we have 0 is 0, 1 to 7 we all know that it is 0, and all the rest are 1s. But minus 1, okay, becomes FF, okay, which is all 1s, okay, and minus 1 to 8 will be 1 and all 0s. What we have done is this column, which is, as you see, I wrote them under each other, okay? As you can see, we have used this, see, this bit is always 1 to indicate, okay, that this is a signed number, and we're using this range, this bit, to indicate that we have a negative number. If you had to subtract 1 okay, from this, okay, so -1, it will become FFFFF, okay? So, sorry, not, it will become 2 Fs, so 8 ones, okay? So this is how we, I'm going to expand on this, okay? For now, I just wanted to visualize a bit so that you can see it. However, what I set for 8-bit applies for 16-bit, okay? So we have the signed bit 15 used for signed, and the same thing can be for a 32-bit long word, okay? So we use bit 31. So that is in relation to, I will continue on the book, but that's maybe some people seeing it will understand it better. So let's jump to the book. So how do we, Fabio comes with two methods of how we can do two's complement. I only like one. The other one, I don't like it that much. And it's quite easy. So basically, okay, you turn all the zeros, in this case, let's say we have plus 26, to make it minus 26, okay? You turn all the zeros, okay, into 1, all the ones into zeros, okay? And then the answer of that, okay, you do plus 1. And he is going to show it, okay, in fact, down here. So we converted them, okay? Where was, can I see them both? Yeah, like this. No, trying to do too much. Yeah, anyway, this number is this number flipped, okay? So where is 0 is a 1, and where is 1, it becomes a 0, and it is here. Then he adds 1 to it, and we get the 2's complement. And that is method number 1. He is referring to it also here, Sistema 1, which is system 1, okay? Method 1, okay? I will come to method 2, but that is how we do 2's complement. The same method will work with long word, and with byte, okay? Here, this is where the table is. He gives the ranges for signed and unsigned, okay? So first one, yeah, that one is for signed numbers. That means that we have plus and minus in the range, okay? While this one, the second one, we do not have, it's, the numbers are always treated as a plus, okay? And it continues like this, okay, for word and long word. And as I said, long word signed numbers are 2 million and 4 million when they are not. It's 400 whatever. I'm just confused right now. But anyway, I said 2 million, but it is more than 2 million, 214 million, no? 1, 2, 3, 4, 5, 6. Yeah, actually, trillion. What is after million? Trillion? We basically take the same byte. I mean, a byte is from 0 to 255, but we divide it. But it's us. For the computer, it's still a binary number, but we just decide that the bit 8, sorry, bit 7 is our sign number. That's why I showed that's why I showed the on my whiteboard. That's why I showed that bit. The high bit was always a 1. No, the course did not restart. So good question actually, Proton. This is where, as I said before I started, I did not agree with this. So the book, I'm just going to say a bit of history about the book. Okay, the book was from chapter 1 to chapter 7. Then Fabio took a break, it looks like, and then he started again, and we are in chapter 8. However, he realized that in the first chapters, he did not cover the status register because he didn't go into the depth of the 68,000. So now he's explaining it. So we were using the compare and the branches, etc., without really knowing exactly the depth of the branches of the flags, sorry, or the conditional code register or flags. So that's why he's covering it here. But what I did not agree also is because instead of taking this part and making it a chapter on its own, he made a long chapter, which is chapter 8, with lots of things in it. And this is one of the sections that talks about the flags, basically. In fact, I will not finish it today because he goes into quite depth of the flags and how, how they behave themselves. But yeah, it is something that normally this is covered at the beginning, not in the middle. So that's why I think he was not going to continue the book. There was a time when he was, he arrived to chapter 7 and he said, okay, had enough or something like that. And then he continued. So also the book is like divided in two sections. It's divided like beginner sections, so from chapter 1 to chapter 7, and then advanced section from chapter 8 till the rest. There's also a third section which is about mathematics, but yeah. So that's the a bit of history about the book. However, I'm going to mention it in a minute. There's he decided, after he realized what he did, to write another book, which is called the 68,000 book, and he will make reference to it. So it's quite a good book. He goes into very detail of how explaining the instructions and how the flag registers behave and everything. For somebody that is doing games or demos, is quite good, but it is a separate book from this one. Yeah, I agree. Most of the time is that what we use, the word more than anything else. I just wanted to keep it simple with a byte. But in the Amiga, most of the time, that's what you will use, I assume. So, in fact, here he's saying what you practically said, Proton, that although there is the byte which is -128 to +127, most of the time we use the word for signed numbers. So I have explained the first method, okay, which is you convert them you flip them and then you add 1. That is system 1. And then there is the second method where you start converting a number, but then you do not flip the last. So basically, I wish we had the other one on the same page. So we start converting the number, okay, and we swap, let's say, the last two because of the plus one. I do not like this second method. I find it confusing, to be honest, personally, but maybe some people prefer this method. In fact, he doesn't. He just says it there, and I think he also preferred the first method because in the first method he explains it more in detail, and the second one is just this sentence and nothing else. If our numbers don't go in minus, then we use, of course, as I said, from 0 to 255. But if they do, let's say from minus 50 to plus 50, then we need to use the branch if greater than, let's see where he's mentioning them. Here, these three and this one. Okay, branch if less than and equal, and branch if less than. Now, what you need to know, okay, is it's the last sentence which is important here. For addition and subtraction, okay, we have these instructions. Let's say via compare, because it's a compared as a minus, basically. When it compares one another by doing a minus. But when we are doing multiplication and division, there are specific instructions. Okay, one is MULU, okay, which you see here. Okay, this is for unsigned numbers, and the same for division. And then we have for signed numbers, MULS and DVS. So when you are working with doing multiplication or division, you need to make, if you need signed numbers, you need, or unsigned numbers, you need to decide which one you need to use. Now he's going to explain the characteristics of each flag. Okay, so the carry flag, bit 0, okay, is when we, let's say we're adding two numbers like in normal maths, okay, if a number is greater than 9, it becomes a 10, then we are setting a 1, no? And it's the same thing with the carry, just to give you an idea of why we have the carry. But if we are doing a minus, we are doing a subtraction, we also borrow. So the carry is used in both ways. And later on we will see examples of this. Also, the carry flag can be set if we are using shift. Let's say if we are shifting or rotating, okay? Any of these instructions. Here he is giving a long number, okay, the maximum that we can have, okay, and if we add 1 to it, of course the 0 will become 0, so the carry flag will be set, and the 0 flag, which I will discuss in a minute, will be set because the value of the 0 is 0. But so 2 flags are set in this condition, and then you do decisions based on that. Overflow is set when a number doesn't fit in the range that we have, okay? So if we have signed numbers and we know that we have from 0 to 127 and -1 to -128, if we are adding an 80 plus 80, so both of them are plus, which is 160, then the overflow flag will be set. So, and it's the same thing if we are, instead of byte, we are using word, etc., etc. So if the number doesn't fit, or if we are using signed and it doesn't fit, then the overflow flag will be set. The 0 flag, I think, is one of the easiest of all. If the result is at 0, then it is set. If it is not, it is not set. The bit 3, which is the negative flag, when the high bit, whether it's a byte, whether it's a word, or whether it's a long word, is set, then the negative and the n bit reflects that. I'm trying to see if I have something, guys, in my notes related to this. No, that's all. He says the same thing basically. This one, the last one, bit 4, the extended, the X, this normally is a copy of the carry flag, okay, but is also used for binary coded decimal. So when we are, instead of using hex numbers or binary, we are using decimal numbers, so from 0 to 10 instead, from 0 to 9, instead from 0 to 15, and the numbers are represented, come on, let me select, anyway, I am indicating it with the mouse pointer, okay. If we have 20, okay, 20, so the high nibble of a byte will be 2, as you can see, and 0 will be the low nibble. For doing binary coded decimal addition and subtraction, you need to use the relevant instructions, okay? So it's ADX and sub X, okay? They have an X at the end, not add, okay? It's when you cannot use add and sub. Now, this is where I said that he wrote another book about the 68,000. First, he called it 68,000.txt. He never converted this into a PDF. Okay, so it's not, you will not find this as a PDF. And then he updated it to 68,000-2.txt. So if you want, you can, you will not be able to Google translate it all. It's quite a long book, but you can do bits of it and find, let's say, the instruction that you want and do Google Translate of it. It's a very, very long book. He is insisting that from before you continue reading the book, you look at a book which is about 68,000, because either you read his 68,000 book, or you get one of these books and read that, because actually you need to know how the 68,000 work to be able to continue. Now, this is where I ended yesterday, but I just need to explain something, okay? There are a series of examples, okay? I don't know if Proton knows that Bringer and the Darkoder was very famous, as far as I know. I remember him, but... And the examples that follow in the book were written and given to Fabio by the Darkoder, to be honest. And there are quite a lot of them, which they are examples which I will cover in the next episode, of how the 68,000 were. They are specific examples, and they show what the flags, how the flags are changing, and which we will do. I mean, it doesn't make sense to start them and finish in the middle of them, so that's why I do not want to start them. Thank you very much, guys, and so ciao, have a good week.